What's going on, guys? Today I'm going to be showing you the beginner's guide for the Diels-Alder reaction, and I'm really just going to show you the only 3 steps that you have to know to solve these problems. And make sure to stay tuned to the next video because we're going to be going over some more advanced ones. Let's go. Alright, so to kick off this guide, I want to first explain what the Diels-Alder reaction is. And basically it's going to be 2 molecules, a diene and a dienophile, reacting with each other to form an end product that's going to be a combination of both of them. And so before we jump into this reaction, I want to first point out 2 important things that I want you to take from this video. One being that every Diels-Alder reaction can be summarized into only 3 steps, and if you can memorize these 3 steps, you're going to be good no matter how complicated the Diels-Alder reaction is. And 2, every Diels-Alder reaction is going to end with at least 1 double bond. So if you don't have any double bonds, you're going to want to look back and see what you did. Alright, so to hop into this reaction, the first thing that I always like to do when approaching these problems is to count all carbons directly touching the double bonds on the diene and the dienophile. So if we count 1, 2, 3, 4, 5, 6, we know that we have 6, so that's why we know that we have a 6-membered ring. And this kind of just helps predict the end product a little bit better. So when I say directly touching the double bond, it means that if there was an attachment here and here, or even here, these carbons would not count because they're not directly touching the double bond, such as these 6. Alright, similarly, I like to number all the carbons, and the carbons that I'm going to be numbering are only the ones that are directly touching the double bond as well. So 1, 2, 3, 4, 5, and 6. And do the same thing on the product side. 1, 2, 3, 4, 5, and 6. Okay, so from here, we're going to jump into the reaction, and these are going to be the 3 key steps that you have to memorize in order to be able to solve any type of Diels-Alder reaction. So first, carbon 6 is going to attack carbon 1. This is going to make a single carbon-carbon bond between carbon 6 and carbon 1, and that's why we see these 2 connected on the product side. Then from here, because carbon 6 attacked carbon 1, there's not going to be enough space for this double bond to stay here any longer. So it's going to move over the carbon between carbons 2 and 3. This is the second step out of the 3 key steps that we have to know. Then from here, because the double bond is between carbons 2 and 3, this double bond, carbon 4, is going to attack carbon 5, creating another single carbon-carbon bond between carbons 4 and 5. And that's what we see on the end product. Okay, so let's go see what we did with all the arrows, the 3 key steps. So first we have carbon 6 attacking carbon 1, which made a sigma bond, or a single carbon-carbon double bond between carbons 1 and 6. Then we see this double bond move over between carbons 2 and 3. And that's how we know there's a double bond between carbons 2 and 3 on the product side. That's the second step. Finally, because this double bond moved over between carbons 2 and 3, this double bond has to move over and it attacks carbon 5, creating that single bond between carbons 4 and 5. So this is going to be the first reaction that we're going to go over today, and they're going to get a little bit more trickier, but bear with us, and you'll be able to solve Diels-Alder reactions a lot easier. Alright, so to start with the second problem, we're going to be looking at these 2 molecules right here, and we're going to start it off the same way we started off the last one. So we're always going to want to count the carbons that are directly touching the double bonds. So we see we have 1, 2, 3, 4, 5, and 6. And you see that I won't count these carbons because they're not directly touching the double bonds, like these carbons right here and these 2 right here. So if we go and number them, we get 1, 2, 3, 4, 5, and 6. So using our little trick, we know that we're going to have a 6-membered ring. So let's go in and draw the 6-membered ring on our product side. Next, let's go in and number the ring as well, just to get that out the way. Okay, so similarly to the last one, we're going to go in and draw a mechanism now. So we always start with carbon 6 attacking carbon 1, pushing over this double bond between carbons 2 and 3, which causes this double bond on carbon 4 to attack carbon 5. So now let's see what happened with the reaction. Carbon 6 attacked carbon 1, and that's why we see carbon 1 and 6 together on the product side, because this is forming a single carbon bond between 1 and 6. That caused this double bond to move over between carbons 2 and 3, so we know that there's going to be a double bond between carbons 2 and 3 on the product side, right here. Now, and this is why it's so important to number your carbons, so you can just compare the reactant to the product side. So next, what happened, because this double bond moved between carbons 2 and 3, this double bond from carbon 4 attacked carbon 5, which is why we ultimately see carbon 4 and 5 together. Okay, so now that the reaction is done for, we can look back and account for these two attachments that we did not account for through the problem. So when we're starting, what I like to do is just to find the carbon that has an attachment on the reactant side, so carbon 1, and then find the same carbon on the product side, and then just put on your attachment. So we see that we had just a methyl group on carbon 1, so we can find carbon 1 on the product side and just put the methyl. Next, we can do the same thing for the dienophile. Find the carbon, so it's carbon 6, then find it on the product side, and then it's the methyl, so just attach the methyl. Okay, so we would be done here. However, there is some stereochemistry involved, but I'm going to show you some quick tips and tricks to be able to understand it a little bit better. So when we're looking at the stereochemistry, we'll start with the diene. Okay, so the diene stereochemistry, in my opinion, is a little bit easier to understand, and there's two different ways that we can look at it. So first off, if the attachment on carbons 1 or 4 is facing upwards or downwards, like this, we're going to know that the attachment is going to be on a dash. Think about it. Up or down, it's away from you. It's going upwards or downwards. It's going away from you, so it's going to be facing the back or dash for stereochemistry. However, if the attachment was facing inward like this, then it would be wedge. Think about it. It's inward, so it's closer to you. This is how I like to remember it. So for this case, we're looking at carbon 1 having an attachment, and it's going up. So up or down is dash, and because this is going up, we know that it's going to be dash on the product side. So we can go in and erase this, just draw a dash. So for the dienophile, it's a little bit more tricky, but in this case, we just have a methyl. So it can be either dash or wedge. And the tricky part about this is that there's actually names for both of these products. So I'm just going to draw them both out for you. So now we have one of the attachments on dash and one of the attachments on wedge. This is going to be known as your endo product when you have your carbon 6 attachment on a dash, and this is going to be known as your exo product. Now these are both answers to the problem, and they would both be correct, but it's going to come down to what your professor asks for. If they ask for the exo product, if they ask for the endo product, or they might even ask for the major product. And again, just make sure to look out for what they ask for, because technically these are both products of this reaction, but they might ask for endo versus exo. Alright, so to get started with our last problem, we're going to be looking at these two molecules right here. And again, we're going to start off by doing the same thing we've always been doing. We're going to number our carbons that are directly touching the double bonds. So 1, 2, 3, 4, 5, and 6. And again, we're not counting this carbon, this carbon, this carbon, or this carbon, because they're not directly touching double bonds. Alright, so because we have 6 carbons that are directly touching the double bonds, we're going to go in and draw our 6-membered ring. And we'll actually go ahead and number this as well. 5 and 6. Alright, so then from here we can start drawing out our mechanism. So first we always start with carbon 6, this being step 1, attacking carbon 1, which is why we see carbon 1 and 6 connected. And then from here, this double bond is moving over between carbons 2 and 3, which pushes over the double bond from carbon 4 to attack carbon 5. So if we run through this mechanism, we see 6 attacking 1, which is why they're connected. This double bond moving between carbons 2 and 3, so we can go in and draw our double bond between carbons 2 and 3. And then the double bond from carbon 4 attacking carbon 5, which is why carbon 4 and 5 are connected on their product side. Okay, so then from here, we can go in and find our attachments and put them in on the product side. So first, let's start with the diene. So we have carbon 4 with an attachment, a methyl group on it. So from the last example, we learned that if an attachment is up or down on carbons 1 or 4, it's going to be on dash. However, for this example, we have a methyl group facing inward.
So we know that's going to be a wedge. So we can go in and find carbon 4 on the reactant side, find it on the product side, and then draw it in on a wedge because it is facing inward on the dyene. Let's go ahead and make this a little bit bigger just to make it easier to see. Alright, so then from here what we're going to do is look at the next attachment on the dienophile. So here we have two attachments, one on carbon 6 and one on carbon 5. So this is where it gets a little bit tricky, but just bear with me. So this double bond is going to be a trans double bond. And I'm going to explain to you what a cis and trans double bond is and the relevance to Diels-Alder reactions. So a cis double bond is going to be a double bond with attachments on either side that are actually facing the same way. See how they're both facing to the right? So this is going to be a cis double bond. However, a trans double bond is going to be a double bond with attachments facing opposite ways on either end. So one going to the right and one going to the left. So if we look at our dienophile, we see we have a carbon 6 attachment going to the right, and then we see the carbon 5 attachment going to the left. So we know this is going to be a trans double bond. And when we find trans double bonds and the Diels-Alder reaction in the dienophile, well, we know that their stereochemistries of this attachment and this attachment are going to be opposite. So if one is on wedge, the other is going to be on dash. If one's on dash, the other one's going to be a wedge. So if we find carbon 6 on the reactant side, find carbon 6 on the product side, and we go in and plug in our attachment. And let's just decide to put this on a wedge. So if that's on a wedge, then and it could also be on a dash. That's not what's important. The important part is that whatever this attachment is, either wedge or dash, this attachment is going to have to be the opposite. And that is because this is a trans double bond facing opposite ways. So now we find carbon 5 attachment on the reactant side and some methyl. So we find carbon 5 on the product side and draw it in as the opposite of this carbon. And again, because it's trans configuration. If this right here was a cis configuration, such as this, then both attachments are going to be on the same side. So either wedge wedge or dash dash. But again, in this case, we have a trans double bond. Alright guys, thank you guys for watching. Please leave any comments or questions down below in the comment section. And please let us know if you have any other topics that you want us to cover. We out!